Hey, Nathan here from PHStudios. Welcome back to another tutorial from the XNA series. And this tutorial is going to cover collision detection, both rectangular and per pixel. And the structure of this tutorial is going to be the overview of rectangular collision detection, then the coding of rectangular collision detection. For per pixel collision detection, we'll do the overview of per pixel, and then the coding of per pixel. So the basic structure is overview, coding, overview, coding. I hope you enjoy this tutorial. I'll see you in the overview. Okay, so here we have two different gameplay objects. And what we want to do with these gameplay objects is determine if they collide. Now, we are using rectangular collision detection in this case, and what you see here are the two sprites. The player is below, it's in the blue, it's the object at the very bottom of the screen, the larger one. The enemy is at the top. It is red, it is above the player, it is facing down, and each of these have a background of turquoise, a rectangular box underneath them. What this box identifies is the rectangular bounds that these objects have. Now, you do not see these bounds. This was done as a visual representation for this overview. And the reason I did this overview was because you can see the actual bounds itself. Now, this might pose a different problem. As you might guess, that we have a wing here on the player, we have a wing on the right side. If the enemy moves straight down, it will hit that wing, and we will achieve a collision, as you can see there. Now, if I lower the opacity of the red's bounds, we can see the wing is not even touching the enemy. This is one of the issues with rectangular collision detection, is that it's not that precise. Another issue with the rectangular collision detection is that you cannot do what you see on the screen right now. You cannot do a rotated rectangular bounds. You can do it if you create your own rectangle class and do a lot of math, but a very simple way to get around this, remove the concept of a rotated rectangular bounds and to transform the rectangular bounds we had before and create the transform matrix, scale, rotation, position, and create the maximum bounds that can cover. Now, expanding on the previous issue, you will see that in front of the player, where the turret is facing, we have a giant gap that is just the rectangular bounds. That means if an object simply enters the top right of the player's bounds and exits, like it's flying past it, we will have a rectangular collision detection. Even though it's going the opposite way, it's just going to touch that single pixel that's in the top right. This is one of the issues with the rectangular collision detection, is that we can't go further in depth. We get many false positives with rectangular collision detection, but it is so simple to use this technique that you really don't get any performance issues with it, and you can just do rectangle.intersects with rectangle. Okay, so now that you got the concepts, let's look about the coding. And the coding is very simple, like I mentioned in the last part of the video. All we have to do is see if rectangle intersects with another rectangle. That's all we have to do. And I'm using my gameplay object class, the version 2, so I can draw the bounds. This is available in the gameplay object 2. You can draw the bounds and it'll display it for you. Okay, so I decided to use these sprites as an extreme example, as expanding on the issue I mentioned before about the very serious concerns about lots and lots of false positives with this technique. So these images are just a large circle, and they're moving. They start a large circle and a diamond, and they start in opposite directions, and they move towards each other. And I used the bounds displaying to show you what happens when we use rectangular collision detection. So let me just press F5, and as you can see here, these objects are moving closer together. Now, what's behind the circles are the bounds. So the bounds are getting closer and closer, and I'm going to release the mouse and the game will resume. When the collision occurs, it will pause for 1 second and remove the objects. Let me show that one more time. So even though the objects did not touch each other, their rectangular bounds did. So all you have to do is gather a rectangular bounds of the object and see if rectangle dot intersects with another rectangle. How did I get that bounds? Well, as I mentioned in that video, when you rotate an object, by default, whatever is included with XNA, you cannot have a rotated rectangular object. Now, you can create your own, but that's going to take a lot of work and mathematics to do so. What I did is I calculated a maximum rectangle that can fill out the image, even though it's rotated, scaled, and positioned differently. Now, that bounds might be massive, but it is better than spending several hours or weeks trying to get a rotated rectangular bounds going. So this is built into the gameplay object class. If we go and look at the calculate bounding rectangle, I use a transform, the vector2.transform function, and I transform the left top, left bottom, and right bottom by the transform matrix of the object, and then I get the new left top, left bottom, right bottom, but I need to determine the minimum and maximum of those and return the absolute maximum rectangle that can support this image. Now, how do I calculate the matrix? I have a transform matrix built into the gameplay object class, and we create translation, and we use an origin. The origin is built into the gameplay object class as well. This just determines, if you've watched my basic training series, this determines how the object is drawn. Default the origin as at 0, 0. It might be changed, it might not, so better be safe, because this is an object, this is an abstract class, so I better be safe to translate it by the origin in case it has been changed. Then I create rotation Z by the rotation value, create scale, static scale value for right now. You can change this for a scale variable, and then I translate it based on the position. And that's all I have to do to get these rectangle bounds updating. If you played my Space Shooter series, Space Shooter tutorial, you will notice that if you enable the rectangle bounds to be displayed like I did here, you will notice the bounds do not look at all like where the object is. That is because I do not do that in that tutorial. Because it was not implemented yet and I did not want to go that far in depth on the transformation matrices and all the other calculations that needed to be done. So you can download this gameplay object CS file. I mentioned it in previous videos. It's on the forums, or I'll put a link on it on YouTube. And now we're on to per pixel collision detection. I'll see you in the overview. Okay, so one of the biggest issues with the previous algorithm is it was not very precise. We will get a lot of false positives with this technique. Now, per pixel collision detection will allow us to look at every single pixel of a specified image and compare it to a different image, and we have two color values that we used. Now, we need to compare those two color values and see how they differ. Lots of people like to use the alpha values, so we're not comparing two transparent pixels. Now, we have an area here that is condensed into 8 pixels. We can check those 8 pixels, and this is done by a simple technique that if we use a game that has no rotation, no scaling, no modifications to any of the sprites except for the location, we can condense the area of focus to that specific point there. Now, this is not a very good technique for later games, so I want to discuss a more complex algorithm. And of course, the more complex, which means the more time the coding will take, and the more performance that will be used. So here is the algorithm that we need to use here. We have two objects. They are overlapped and we need to test the per pixel collision detection. So image A, which is the bottom one, we need to test the per pixel collision detection starting at 0, 0. That lit up area right there. Now we need to test that same location inside of B's space. So 0, 0 relative to A, we need to remove that from A's space. We need to send it to the world space, which is the background of black, and then we need to add it to B's space, which is lit up right now. Now this result means that it is not inside of the array and we can ignore it, which means there is no valid collision because we cannot test B. Therefore, we can just ignore that. Now, the issue we have here is that if we do it that way, we need to test the next pixel. And if it's outside of the array, we need to test the next pixel. And we could potentially look at every single pixel of image A and not have any collision. We can do that several times until there is a collision, or sometimes there might not be a collision. It just might be barely close to an intersection point, but the only overlapping was that transparent pixels. Okay, so now I'd like to talk about the algorithm inside of the coding now. I hope you got a good understanding about this. This is a very complex thing we had to do. Just remember that we're looping through every single pixel inside of image A, which is the one below this one we see here, the one towards the bottom. So we have to loop through every single pixel of one image of our choice. I chose A. That can be the bottom one. And at the start, we need to look at position 0, 0. So we loop through every single pixel of a dedicated texture. we need to remove that pixel location from that texture, send it to the world. So we need to use the matrix inverse of the other texture. So we need to send it to the world, which is the game window. Remember, 0, 0 relative to the texture is just the top left pixel. But on the world, it could be 20, 50. So we need to send it to the world to get that 20, 50. And then we need to send it back into B space. And that will give us that little lit up area that you saw that was to the left of this box, and it was outside of the texture array. The texture array is what you see here. It was outside of that array, so we could not test it. We would have received an array index out of bounds error. So I hope you get a good understanding, and I'll discuss this a little bit more in the coding. Whew, are you still with me? Per pixel collision detection is a very complex thing, and to throw transform matrices and transforming it to the world then to a different matrix, that can be a little confusing. Not to mention this code here that I will not go that far in depth on. Let me get to the algorithm here. This coding is a multi-threaded coding, and I did it this way so I can have a visual representation of where the first thing that can work for A and B, the first pixel choice, the first one we can compare, valid, from A to B will be marked in a white dot. When there is a collision, the background will be red, and we will see the point of collision as a white dot. So this is what I did the threading for, so I can get that callback and to get a visual representation of what we see. Okay, so this is the single-threaded algorithm. As I said before, we have position 0, 0 first. We need to transform that from A space. Remember, position 0, 0 is relative to A. A has its own transform space, matrix space. B has its own space, and the game window has its own space. So we need to remove that from A space and move it to B space and get that result. So what we need to do is we need to calculate a matrix A to B, from A to B. So we multiply the A transform, multiply that by the inverse of B transform. Now, we need to loop through every single pixel in A. I chose A as the guinea pig, so to speak. So we look at every single pixel in A, and we loop through, we move one column and one row every loop. Of course, I do it by columns, so I'll look at 0, 0, 0, 1, 0, 2, so I do it based on columns. So I go from top to bottom, then left to right. Now, that is 0, that moves from 1 down and 1 right. So we need to do the same thing in the other one, the B's transform. So we need to calculate the step X and step Y. So instead of 1, 0 and 0, 1, we need to calculate the normal using that A to B matrix. So we have two for loops here. We're incrementing it by 1, so we can look at the next pixel adjacent to the one we just looked at. We need to do the same thing with B, so that's where the step Y and step X come into play. Now, like I said before, we need to calculate the initial B position. Vector dot 0, which is 0, 0, is an A space. We need to move it to B space, so we use that A to B matrix. There is our 2 for loops. Now, as you saw in that video overlay, we check to see if that value that we got from A to B is a valid value, which means, is it inside of the array? In that video overlay, we looked at a pixel. It was lit up as 0, 0 inside of A's space, but in B's space, it was outside of the array. So this is what that checks here. If it's inside of the array, we can check inside of the array. Now, if you want to use this for yourself, you want to do something like this. I'm actually not using the single threaded method, so I could just show it to you this way. The reason I had it the other way is because my images, they have a gray background that are semi-transparent but not fully transparent. So if I left it the appropriate way, which was this way, it's basically a rectangular collision detection at this point, but it's a more complex one. So this is the way you actually want to do this. Do not have a semi-transparent background of the entire image. Otherwise, you'd have to do what I did before. But you get the idea. If both of these have an alpha value above 0, which means we have 2 semi-transparent or fully visible pixels that have collided, we have a valid collision detection. So we return true. Otherwise, after the 2 for loops, we return false. Okay, so that was the algorithm. I'm not used to this new mouse. I'm sorry if I'm jumping all over the place. Okay. Now the threaded algorithm is just going to give us a callback. I used a reporting code and I used thread.sleep and I stopped the algorithm from running for that specific amount of time. And this is multi-threaded, so this thread stops, but both the drawing code and the update code still works. I forgot to mention before, per pixel collision detection is a huge performance decrease. It is a performance hog. I have 2 for loops. It's going to loop through potentially, it's going to loop through the entire texture multiple times before it finds the collision. And it might not find the collision. As I mentioned before, we can go into this collision detection and it will just overlap the transparent pixels and then they will leave each other's rectangle bounds. So it can overlap each other and we'll check the per pixel collision detection, but it might not actually return true. So the issue, since this is so slow relative to rectangle collision detection, it is always recommended that you do this after you have a valid rectangle collision detection. So check the rectangular collision detection first. This will throw the per pixel collision detection. Okay, now for the result. As I mentioned before, this is a multi-threaded application. It is going to give us a callback feature that will identify the point in A and point in B that should be the same point. That will give us the point of testing, that we tested both pixels. And I return the B's position. If it's a valid point inside of B, I return that. This will be the first valid point, which means we can test both A and B's texture data. It's not outside of anybody's bounds. We can test it, so you will see a white dot, and this will identify the first available point of testing. Now, if it's a valid collision, the background will become red, and it will display that point of collision in white, and it will sleep for a certain amount of time. So, let's go ahead and watch. So, as you can see, that white dot, there's that point of collision. Now, this algorithm is not that slow. This is that thread.sleep, just to give us a callback and we can look at it. So do not worry about the algorithm taking this awful lot of time. That's not what's going on here. Can you see that white dot just yet? Wait until they come back. There it is. It's towards the top of the red. There we go. There's a collision point. And let me just go ahead and remove the reporting code of this. And just show the reporting code of the collision point. Now we have the collision point right there. Right there. Right there. It might be hard to see, but once you'll notice where it is and how to look for it, you should be able to see it all the time now. So the very tip of... Wait for it to come back. There we go. The bottom, the right side of red. There you go. Right side of red, or left side of red. Bottom. Alright. So, that was the per pixel collision detection with the visual representation of where the collision point was. Alright, so I hope you understand everything. If you want to see this code, you're welcome to. I'll package it up and clean it up a little bit more and let you have a look at it. It's multi-threaded, but it's a visual, it's a tutorial type of coding. So I put thread.sleeps here, and I put in a callback, which will call back to here, which will set the A and B's pixel point, and we can draw it. Okay, so this coding will be available to you so you can see the visual representation. I will release the other code, single-threaded version, and no slowdowns at all. You can see that it runs very smooth. And I will release the rectangular collision detection code as well. And you will have access to the gameplay object as well. So you will have access to a lot of downloads, and we will go from there. So that's it for this tutorial. I hope you enjoyed it, and I hope you learned something. I hope the per pixel algorithm and discussion, I hope you learned something from that. It's a pretty complex algorithm and pretty complex topic. So I hope some of you got it. Next tutorial will be later today, and we will discuss the After Effects. We will do the 2 tutorials. We'll finish that series off, and Then we'll have a site announcement later today as well, and I'll discuss some things. So I hope to see you next time.